We continue with semi-inverse solutions in the third part of the lecture. Here we have another example. It's a prismatic bar under axial loading. By prismatic bar, I mean a bar that is fixed to the ceiling from a surface. Again, we're seeking to calculate a stress, a strain, and displacement for any point x1, x2, x3 in this linear elastic prismatic bar. We assume a uniform distribution of a stress over the top surface, but the displacement is 0 at this point. So we have two assumptions: uniform distribution of a stress and fixed displacement at the top part. Pay attention, we're seeking a solution away from the support region, so we don't concern about the exact stress distribution there. This is basically based on the Saint-Venant's principle that we discussed before. Okay, the first step is drawing a sketch of the problem, indicating all of the forces. As you see here, we have gravity acting on the material. We have the fixed end at x3 equal to L with 0 displacement, and we don't have any other forcing. And we assume that the reference frame is at the bottom. With x1, x2, and x3. Okay, the second step is calculating stress boundary conditions using the relation between traction and stress. Everywhere on the boundaries, we don't have any stress except at the top where the bar is connected to the ceiling. And there we have a uniform stress opposing the weight of the bar. If we assume that the density of the bar is gamma, we can say that at x3 equal to L, we have a traction equal to gamma L multiplied by the area, which is BD, again divided by the area. So this is volume, this is area. And pay attention that we can basically cancel these two. And this traction is upward, so it's 0, 0, 1 for the vector. The normal vector to that surface is again upward, so it's going to be 0, 0, and 1. Now let's use the relation between traction and stress. For that surface, we get T1 equal to sigma 1, 1, and 1 plus sigma 2, 1, and 2 plus sigma 3, 1, and 3. N1 is 0. N2 is 0, N3 is 1, so sigma 3, 1 is equal to gamma L. For T2, we have sigma 1, 2, N2 plus sigma 1, 3, sigma 2, 2, sigma 1, 2, and 1 plus sigma 2, 2, and 2 plus sigma 3, 2, and 3. Again, N1 is 0, N2 is 0, oh, sorry, it's going to be 0 here. Okay, and so sigma 3, 2 becomes equal to T2 and T2 is 0. For T3, we have sigma 1, 3, N1 plus sigma 2, 3, N2 plus sigma 3, 3, N3. Again, N1 is 0, N2 is 0, N3 is 1. So sigma 3, 3 is equal to T3, which is gamma L. Okay, by considering the boundary condition at other locations, for example, at x3 equal to 0 or at x1 and x2 equal to b divided by 2, we can say that a stress-free everywhere else. So sigma 1, 1 is the same as sigma 2, 2, the same as sigma 1, 2, 0. Also, note that the body force is equal to minus lambda, minus gamma, which is the density multiplied by gravity. Let me note it here as well. Density multiplied by gravity. Okay, we found that at z or x3 equal to L, we have sigma 3, 3 equal to gamma L. The third step is obtaining a distribution of the stress tensor that satisfies all of the boundary conditions and all of the equilibrium equation. This stress tensor should give us sigma 3, 3 equal to gamma L at x3 equal to L or z equal to L. But we know that everywhere else the stress is proportional to the length of hanging a material. So for example, at any location with x3, the stress will be probably something like gamma x3, proportional to the material hanging underneath. So one good guess for the stress tensor can be one with all of the elements being 0 except for sigma 3, 3 as gamma x3. So basically you have to guess it yourself here based on the condition, and that a good guess that satisfies all of the boundary conditions simplifies our solution a lot. Okay, now we have a valid stress tensor. The next step is calculating a stress tensor using Hooke's law. Let's do it. For epsilon 1, 1, we have 1 over E 1 plus mu multiplied by sigma 1, 1 minus mu delta 1, 1. Sigma kk is the trace of a strain tensor, so it is basically sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. We know that sigma 1, 1 is 0, delta 1, 1 is 1, sigma 1, 1 is 0, sigma 2, 2 is 0, and sigma 3, 3 is gamma x. So it says epsilon 3, 3 is minus mu divided by E multiplied by gamma x3. This is x3. For epsilon 1, 2, it is 1 over E 1 plus mu sigma 1, 2 minus mu delta 1, 2 sigma kk, the trace. We've already calculated the result of that. We know that sigma 1, 2 is 0, delta 1, 2 is 0, so it is basically equal to 0. The same for epsilon 1, 3 and epsilon 2, 3. For epsilon 2, 2, we have the same as epsilon 1, 1. It becomes minus nu divided by E gamma x3. And for epsilon 3, 3, we have 1 over E multiplied by 1 plus mu sigma 3, 3 minus mu delta 1, 1 sigma kk, the trace. Sigma 3, 3 is gamma x3, delta 1, 1 is 1, and sigma kk, the trace is again gamma x3. We have minus nu here and plus nu here, so they cancel each other, and we end up with epsilon 3, 3 equal to 1 over E multiplied by gamma x3. Now we have all the elements for epsilon, and you know that the body force is equal to minus gamma. The epsilon becomes a diagonal matrix with off-diagonal elements becoming 0, and epsilon 1, 1 and epsilon 2, 2 related by Poisson's ratio to epsilon 3, 3. The fifth step is checking that the compatibility conditions are satisfied. Again, they're automatically satisfied this time because we have linear strains. So this time the strain is not constant because they're a function of x3, but they're linear. So again, they're automatically satisfied. The sixth step is calculating the displacement field using the kinematic equation. Let's do that. For epsilon 1, 1, we have it's equal to u1, 1 or partial u1, partial x1. And we know it was equal to minus nu divided by E gamma x3. So if I integrate that with respect to x3, I get u1 equal to minus nu E gamma x3 x1 plus a function of x2 and x3. Again, it's a constant, but can be a function of x2 and x3. For epsilon 2, 2, the other non-zero element, we have equal to partial u2 partial x2, again equal to minus nu divided by E gamma x3. We get exactly the same result for u2 E multiplied by gamma x3, this time multiplied by x2, plus a constant which can be a function of x1 and x3. For epsilon 3, it is partial u3 partial x3, which is equal to 1 divided by e gamma x3. So integrating that with respect to x3, we get u3 equal to 1 divided by 2e gamma x3 to the power of 2 plus, this is f2, plus a constant which can be a function of x1 and x2. Okay, the next step is implementing boundary conditions. So for example, we know that at x equal to x3 equal to L, u is 0. So basically u1 and u2 are 0 and u3 are 0 for x3 equal to L. And also because of symmetry, u1 and u2 are 0 for any point along the line x1 equal to x2 equal to 0. Enforcing that, we end up with f1 equal to 0, because basically assuming x1 equal to 0 for any x3, u1 should be 0. Also f2 is 0 because u of x2 equal to 0 is 0. Here it's because u1 of x1 equal to 0 should be 0. But here we have a value for f3 knowing that at x3 equal to L, u3 becomes 0. So basically 1 divided by 2 e gamma L3 to the power of 2 should be equal to minus f3 as a function of x1 and x2. And also at x1 and x2, at any x1 and x2, u3 should be 0. So considering those two, we end up with this relation. I leave the details to you. So basically we considered two boundary conditions here. To work out f3, which can be a function of x1 and x2. And here is the result for the displacement distribution. One important observation here is the displacement at the tip, which is x3 equal to 0, is not uniform, and it's parabolic, with a maximum along x1 equal to x2 x2 equal to 0 at the center, basically, center of the cross-section. Some important points: all points outside the central line, the center line, have contraction in the x1, x2 plane, which is related to the Poisson's ratio. The axial displacement is not uniform on the cross-section. It's parabolic, and it has a peak along x3 axis, and the solution is unique. Finally, remember the methodology that we have followed is called semi-inverse method. Here, the stress field is initially assumed, so it's kind of inverse. Then it is shown that it satisfies the equilibrium equations and the boundary conditions. So basically, we enforce the boundary conditions to find the constants there. And we show that assumed stress field satisfies the traction boundary conditions. Okay, that was semi-inverse method. We have two other methods to talk about: displacement formulation and stress formulation. Displacement formulation. In this strategy, we find a relation for displacement, u as a function of external loading. This is how it looks. You see u is the free parameter here, and we have p loading here, but there is no sign of sigma or epsilon. To find this relation, we use equilibrium equation, constitutive law, and kinematic relation. We've already seen those. Let's start by substituting epsilon from kinematic relation into constitutive law. We get sigma ij is equal to lambda delta ij epsilon kk, which from kinematic relation becomes uk comma k, plus 2 mu epsilon ij, which is half of ui comma j plus uj comma I. Okay, note we have 2 and 2 here. Now we substitute it into equilibrium equation. For that, we have to calculate sigma ij comma j. So we differentiate our relation with respect to j, and it becomes lambda delta ij uk comma kj plus mu ui comma j plus uj comma ij. So basically, when we differentiate u for the second time with respect to xj, we just add index j after comma. Okay, pay attention here. We have j here and here. Delta ij is only 1 for I equal to j. So basically, this becomes I. And so here it is basically u k comma k I. But k is a summative index, so we can change the name with anything. We name it j for simplicity. So it basically becomes uj comma ji. Now note that we have uj comma ji and uj comma ji here. Oops, I forgot to put plus pi equal to 0 here. So we basically can rearrange the relation and get lambda plus mu uj comma ij plus mu ui comma jj plus pi becomes 0. And this is exactly what we already had. Okay, it gives us 3 equations in terms of displacement. They are known as Lamè's equations, or Navier equations, or Navier-Cauchy equations. If a solution can be determined for these equations that also satisfy displacement boundary condition, then we use kinematic equation to calculate a strain, because we've already calculated u, so we can find a strain as a function of that. Then we use constitutive equations to obtain a stress. So from epsilon we find a stress. And finally, we use boundary conditions to calculate integration constants, as you've seen in the previous examples. We're going to see how an example of this in the next part of the lecture.